This video talks about the input signals to our receiver with the different noise sources. So first of all, these pins right here are the connections from our digital board. We have the 3.3 positive and the negative rail, so we're going to convert these to 1.65 and minus 1.65. This is going to be connected to the output of our receiver, and then this is our transmitter signal that we're not using right now. So first of all, our supply voltage has a 3.3 volt with 30 millivolts of noise at 2.6 kilohertz. This is our DC noise. This is our low frequency noise, 60 hertz. This is our high frequency noise at 40 kilohertz. And then this is our signal. So if we run this, the first thing that we want to do is these current sources model our photodiode. So we have to make sure that our photodiode stays reverse biased. So this point here is right around 1.7 volts in this case, and this volt here is right around 0.4. So the difference between these two, so this distance from here to here has to be above 0.5 volts, where this voltage has to be higher than that voltage. Otherwise, we don't have reverse bias diodes and it will stop working. Okay, so then the next one is, if we look at this signal, first of all, you see this wobble through here. That is our 60 hertz noise. If we zoom in on this, you can see from here to here is our high frequency noise. So I can put a cursor here and a cursor there, and you see that this is our 40 kilohertz noise. So if we zoom back out, we also see that there's this little wobble that's riding along here. That's going to be a combination of our signal and our noise. This is called a beat pattern because these are too close together to really see. But what we want to do now is turn off our noise, our signal. So we're going to make that 1 pico. We're going to rerun this. So now, again, this is our 60 hertz noise, our really fast 40 kilohertz noise. And now, since we don't have our signal, we can see that there's this wobble right here, and that's going to be this noise right here. So if I put a cursor on a peak here, and another cursor on a peak about there, you see it's about the 2.6 kilohertz. So this is all noise. So if we go here and look at this noise, we're just looking at the peak to peak. It has a peak to peak of 0.198, and that's going to be our noise signal. Okay, now we're going to go look at our actual signal. So we're going to turn this one off. We're going to turn this one off, and we're going to turn this one off. These are all of our noise signals. And then we're going to turn this one on, which is our signal. So we put in the 40 nano. And then we run this, and this is our signal. So again, if we go look at this, we see that this has a signal of Vs, which is equal to 0.016. So if we go and look at what our end result is, we are going to do V signal minus Vn. So 0.016 minus 0.198. So this is minus 0.182. And this is negative, and we need it to be positive and greater than 0.2. So this number here, the signal minus the noise, has to be greater than 0.2 to meet the spec, and we want it to be as large as possible to be able to get the most maximum points.